Today I'm delighted to welcome back to campus Arun Majumdar as today's speaker in the first of the View from the Top series for the fall semester. The View from the Top series gives the college community a chance to hear from the best of today's leaders and visionaries in science, technology, and business. I'd like to thank the Berkeley chapter of Tau Beta Pi, the Engineering Honor Society, for co-sponsoring today's lecture. Before I introduce Arun, I'd also like to invite you to mark your calendars for another very special event coming to the college on Wednesday, September 12th. We will welcome Dr. Seyumon Inaba, founder and honorary chairman of the FANUC Corporation, and our program with him will include a conversation with a panel of college and industry experts on advanced manufacturing and innovation. And that's September 12th. Same auditorium, same place in this auditorium. 4 p.m. in the Banatao Auditorium. Please check the college's webpage for additional information. Let me tell you a little bit about Arun. In 2009, Arun Majumdar was nominated by President Obama and confirmed by the Senate to become the founding director of the Advanced Research Projects Agency, Energy, ARPA-E, where he served till June 2012. Between March 2011 and June 2012, he also served as the acting Undersecretary of Energy and a senior advisor to the Secretary of Energy. You know, I was in the DOE headquarters yesterday, and they said basically he ran all of energy and in partnership with Steve Chu. So, you know, at one time he had all three titles: ARPA-E Director, acting Undersecretary of Energy, senior advisor to the Secretary. So, as part of his legacy to the Department of Energy, he helped create a vision for ARPA-E to innovate the future of energy technologies, to recruit top talent, and create new programs to translate science into a broad spectrum of potentially game-changing energy technologies. He also set up an organization with a culture of speed, efficiency, transparency, and integrity. You know, these are all messages to take home for ourselves, and it was certainly a model in Washington. His responsibility as acting Undersecretary of Energy spanned not only technology innovation, but also a much broader spectrum covering the whole innovation ecosystem: technology, manufacturing, markets, finance, and business, as well as financial and regulatory policies. Prior to joining the Department of Energy, Arun was the Almy and Agnes Maynard Professor of Mechanical Engineering and Material Science Engineering here at the college and Associate Lab Director for Energy and Environment at LBL. Arun Majumdar, I believe, personifies what we think Berkeley engineering is all about: educating leaders, creating knowledge, and serving society. He has exemplified this mission throughout his career, both in academia and at the highest levels of public service. We are honored to call him one of our own and to welcome him home. Please, Arun, welcome.
Thank you. Thanks a lot. Can you hear me? Yeah. Great. I hope the lunch is wonderful. Dean Shastri, thank you so much for that really kind introduction. And I just want to thank you. It's great to be home. It's great to be back in California. And
please come often.
So I thought I'll give you a view from the inside about a paper that Secretary Chu and I just wrote. And it talks about a new industrial revolution, but I'd like to go a little deeper than that. This is the title of the paper: Opportunities and Challenges for a Sustainable Energy Future. And it came out about a couple of weeks ago in Nature. And I'll go a little off track for a little while to say, to give you a little background on how this paper was written. Nature had contacted both of us independently to write the paper without sort of realizing that we actually talked to each other. So I asked Mr. Secretary, I've been asked this, do you want to collaborate? He said, hey, I've been asked this too, let's just do it. Let's just do it together. And we said yes to Nature without realizing what we were getting into. Because in this case, we did not have our students and postdoc to help us. So we spent, and I had left DOE by mid-June, and I was here, and he was over there. And we were collaborating, and it took the whole month of July to really focus and get this done. And it was done on nights and weekends. And, he would work till, and this is a typical thing that would happen, he would work till about 3 in the morning and email the paper back to me, and with references fixed and all that, and I would go and change a few other things. I would get it at midnight then, because 3 hours. I would work till 4 in the morning and email it back to him, and it's 7 in the morning out there, and then he would work on it. That's how it happened. And once in a while, he would call me and said, hey, Arun, today I can spend only two hours because I got to meet the president today. I got a few senators, and I got a nuclear issue to deal with. What about you? And I had to, heck, how do you beat that? So I had to put a straight face up and say that, I have to walk the dog. I got to pick up my daughter. I have to cook lunch for my daughter. And actually, my daughter is right here. She's doing an internship. And this is actually true. I picked her up out here from Stanley Hall. And Mr. Secretary was on the phone, and the whole trip was discussing about the paper. But that was how it came about. And it was a labor of love for a while. But it's done. So I just want to give you a little preview of what we were thinking and how this was sort of capturing some of our thoughts that we went through, some of our experiences onto document. Now, we were asked to comment on a few other review papers that were also written. And that was the main purpose. And they gave us 1,800 words, and we said that's not going to be enough to write about all of energy. So it turned out to be an 8,000-word paper and still could not capture. And so, for example, in this paper, we did not cover grid. Not that it's not important. It's hugely important. And I'll talk a little bit about that. We did not cover energy efficiency on the stationary system side, which is, with all the apologies to my LBL friends out here, we did not cover it out here. But not that it's not important. We just did not have the bandwidth and the space to do that. So why new industrial revolution? Let's go back in history and see where we have come from, what this industrial revolution that we had was all about. We said the industrial revolution was about from horsepower to horsepower. So if you go back in history in the mid-1700s, this is how transportation happened. It's based on human and animal power. And now if you go to a grocery store in the evening, you carry your 300 horses that take you there. If you want to take a high-speed train, hopefully in the West Coast sometime, it'll be about 10,000 horses taking you there. And if you want to fly across the continent, which would take in about a month or so in the past, you can go in a few hours with 100,000 horses taking you out there. That's the transformation that has happened over the span of around 250 years or so. And this is not just in transportation. Our factories have changed. Our agriculture has been mechanized. And we have CFL light bulbs where Berkeley and LBL had such a role to play, and LEDs and air conditioners. Imagine air conditioners were not even there, till about 1920s or so. This is what the situation was. That's the transformation. And if you look at, in terms of the productivity, this is global per capita GDP has gone up exponentially because of that. And that is primarily based on how we use fossil energy. And if you look at the fossil fuel use in coal, gas, and oil, that has also increased exponentially. Without the utilization of fossil energy, none of this would have really happened. So if you look at the world population, that was per capita. The world population has increased exponentially, and that is also due to technology and would not have happened, at least in the recent past, without something like the Haber-Bosch process of artificial fertilizers, without which we would have probably, the population would not have grown. And so this is where we are today. Technology has really changed our lives. And if you look at the future, the population projections are such that this is the United Nations study that came about, that by the end of this century, we'll have about, the average is 10 billion, but the error bar is also 10 billion. So for all practical purposes, let's assume the average, there'll be 3 billion people added to this, to our population. In addition to that, if you want the GDP per capita growth, the energy use is going to skyrocket. So the question is, do we have the energy to sustain that? So let's talk about oil and gas reserves and production. The graph on top is from BP, and they have looked at what the oil reserves are, the global oil reserves. And somehow you don't see a peak in oil because the technology has improved so much of technology for discovery and access that the amount of reserves that are accessible keeps on increasing. And you go to deeper and deeper water to access oil. I was part of Secretary Chu's team in the BP oil spill. And boy, there's a lot of room for engineering improvement out there. But nevertheless, they can go now to 1 mile to 2 miles, 3 miles deep to grab oil at a pretty low cost. And this keeps on increasing. The global oil production capacity that we have in the next 10 years is likely going to increase. A large fraction of that is going to be in the United States and Canada. Iraq oil is going to come. So if you look at this plot out here, this United States is going to be the second biggest producer of oil. From all the reports that we're hearing, this is what is going on. And this is not just from an academic institution. This is also from the Wall Street guys they're looking at, which means the oil price need not be this high. It actually could come down and may be volatile as well. This is just oil. If you look at gas, this is also from BP out here, and you find the gas reserve. This is global gas reserves without U.S. shale. And that is also increasing, and if you include the U.S. shale, it is a dramatic increase in natural gas production. So in terms of affordable, accessible fossil fuel, we don't have a problem, at least for the next decade or two or maybe more, because the technology keeps on improving. So the question is, what else is going on? Well, I don't have to tell this crowd about global warming. In some cases in Washington, I had to explain. But out here, I don't have to. But what has not been done in the past, which has recently been done, is some correlation between global warming to local climate change. And we always talked about this 0.8 degrees increase in temperature on global average temperature without talking about the distribution of what that temperature of the what around that average. Well, here's a paper that came out in PNAS just this month. This is the 1950s. It's not quite Gaussian, but pretty close to Gaussian distribution. You got 1960s, which is pretty close, 1970s, 80s, 90s, 2000. And this dashed line is a 3 sigma, 3 sigma based on the original temperature distribution, which is fairly stable. And what we're finding is that now the temperatures on a global average, the distribution is such that we are exceeding 3 sigma and reaching 4 and even 5 sigma. This is not normal. So this average moving to the right is what we call global warming. Now we are looking at this. Now the question then one would come up is, okay, so that is the global average distribution. Where does it happen? What is the geographical distribution of this? And this is the geographical distribution. This is 1955, and this dark region is beyond 3 sigma is the really dark region, and beyond minus 3 sigma is the really pink region. So you have 1950s, 65, 75, and now you got 2006, 2007, 2008, 9, 10, 11. And you can see this was the heat wave that was there in Moscow and Russia, which led to a lot of deaths. And this is local effects. Now, it would, you would have these high temperature, and in fact, the summer heat that we had in the East Coast and the Midwest is probably, most likely, an effect of that. Now, next summer may not be as hot. Who knows? But there is no question, is undoubted sort of trend towards these higher temperatures that we are seeing. And if this is 10% of the land mass, ignoring Greenland, land mass being covered by higher than 3 sigma. This is 21% of the land mass covered in higher sigma. This is local weather. This is local changes, weather extremes that are happening. And I really think that we have not done a good enough job in explaining this to the general public. And there's an opportunity out here where this will affect real people's lives. And this is an opportunity where I think there's a public discussion that needs to happen. But I won't go into that. This is what we're living with. So if you ask the question, since I started the talk with Industrial Revolution, how much cumulative CO2 emissions have you had since the beginning of the Industrial Revolution? The numbers are a little debatable, but it's on the order of 1 trillion tons. And if you ask the question, how much more CO2 can we emit, if you wanted to, based on the known fossil fuel reserves of today? And that's about 3 trillion tons more. The number is, there's an error bar associated, but it's roughly 3 billion tons. That's how much we can do based on known reserves today, and those reserves are increasing over time. And this is worth, if you ask the question, how much is it worth based on today's prices of coal, oil, and gas? It's on the order of tens of trillions of dollars. And so that's the debate that we are having. Should we let those $10 trillion of our economy down below, or should we address a different way? And the question that, the conclusion that we made was that there may be a better way. There may be a cheaper way of doing business out here. So we used Sheikh Yamani's line. The Stone Age did not end because we ran out of stones. And we added, because we transitioned to better solutions. And this is not foreign to the United States. This is what happened in the 1890s and early 1900s. In New York, this is what horse carriages used to carry people. And this is what transitioned to in a matter of 30 years. And why? Because 160,000 horses in New York and Brooklyn in 1880 were producing 3 to 4 million pounds of horse manure a day. And there was employment, of course, to clean up all that. There were jobs. But we just transitioned to a better solution because it was just a better way of doing business. Okay? So the question is, are there better solutions? And that's going to be the focus of my talk, is that maybe there are better solutions that are cheaper, that are better than what we are doing today. So when we talk about the energy system, there are many dimensions to this system. You could talk about stationary systems, which is electricity-based and natural gas-based, but stationary system where you have energy supply, where you have produce electricity. You have distribution, the grid, not just the electricity grid, but the distribution of natural gas, et cetera. And you have energy demand in buildings and industry, factories, et cetera. That's the stationary system. And you've got the transportation system, which is overwhelmingly based on oil right now. And then, the use in cars and vehicles and automobiles, et cetera. And these two systems are largely independent of each other. They're starting to get connected because of electrification of transportation, but almost independent of each other right now. So this is one plane of this multidimensional energy system. This is one plane. There's another way to look at this system. And that is, if you take each of these bubbles out here and take a technology in that, whether it's electrification or transportation, which is natural gas, electricity production, each of these technologies, think about the third dimension out here. And let's talk about what else is out there. And what is out there in the energy business is that you have to account for cost and scale. Extremely important. So on the y-axis is cost over performance, and the x-axis is scale in size of volume. Energy is not, little things. It's big. Everyone uses energy. It takes a lot of mass, a lot of volume to do that, and scalability is a hugely important thing. And any technology, whether it's air conditioners or LED lighting or CFLs, all follow what is called a learning curve. That is, the more and more you do, the better you get at it, and the cheaper it becomes. And that's part of the R&D between manufacturing, between research, and all that. That happens in an assembly line or in a production line somewhere in a factory here in the Bay Area or elsewhere in the world. That's what happens. And if I look at what DOE does, so let me just map what DOE does. The DOE applied program, so this is technology innovation, this is manufacturing and scaling, this is deployment. So this is now the whole span in that other dimension of technology innovations happening out there. And as you go into manufacturing, the purpose of manufacturing is to scale. And while you do that, you better reduce the cost to improve the performance. So this is what the DOE applied energy programs, like energy efficiency, renewable energy, fossil energy, nuclear energy, Office of Electricity, that's what they do. They try to do research based on science to go down a current learning curve. And you need incremental improvements of that. That's absolutely critical. What ARPA-E was created to do was to create entirely new learning curves. And to do that, you got to translate science. Everything is based on science. But to do that, you have to take some risks because there are chances. You have to create a portfolio of different approaches to create breakthrough technologies. Some of them will fail. We would not know which ones would fail, which ones would not. Those are the crosses out here. And I don't call them failure. There are opportunities to learn, go back into science, and come back again. But there is a chance that one of these technologies would scale in such a way that it'll be better, it'll be cheaper, and better than what is being done today, so that it'll be disruptive to today's technology and it'll become the new learning curve of the future. So the nation as a whole would then go here and have a little inflection point and go down below. So we should always be in the search of trying to find how to beat today's learning curve, because that is innovation, that is global, that's being competitive in the world in trying to come up with better and better solutions. But if you try to do this, there's a role of research to play out here. There's a role of manufacturing innovations that will happen. But as you go down the scale, it costs more and more money. And so initially, in the early stages, we were funding projects. DOE funds projects, typically a few $1 million for a few years. But that's just the early part. Then this has to go and scale, and that scaling is done in the private sector. And then it costs money on the order of a few orders of magnitude more, and it takes time, sometimes more than 10 years, for new innovative technologies to come on board. And so if people think it's going to happen in a few years, they're mistaken. This is going to take time. And of course, the deployment happens, and the private sector has to play a role, and the deployment happens where markets are. And markets are created by demand. Demand could be businesses, could be consumer, could be the US government. The military is the biggest user of energy. And they create a small market compared to the bigger private sector market. Nevertheless, a very useful market, and of course, the global markets. I'll come back to this later on. So let me give you a few examples of potential disruptive breakthrough technologies that we saw when I was there in DOE. So let's talk about stationary energy systems. And I'm going to mix technology and economics because they cannot be separated. Again, the research is done to reduce the cost and improve the performance. So here's the latest data that we had in our paper from Bloomberg New Energy Finance on the cost of electricity, cost of energy in Q3. This is now, 2012, and compared to the reduction in cost compared to Q2. And what is striking out here is these are the different technologies, and here is dollars per megawatt hour. And you find that the cheapest way to produce electricity today is natural gas combined cycle turbines. These are about more than 60% efficient. Natural gas is cheap. You combine them together, and you get about $50, $60 a megawatt hour, which is about 5 cents a kilowatt hour. That's the cheapest way to produce electricity. Well, what has happened also in the last few years is the following. That if you look at wind is actually cheaper than coal, new coal, today. And this is unsubsidized data, without subsidies. So wind, as you become better and better, and these windmills become bigger and bigger, they actually get cheaper. And not only that, if you look at photovoltaics out here, it is about $120, $140 a megawatt hour, or 12 to 14 cents a kilowatt hour. And that is dropping between quarters at a rate of -9%, -8%. Okay? This is amazing what has happened in the PV world. And the question is there room, more room, and could we get solar down to $50 a megawatt hour? And that was the inspiration of why we created something called the Sunshot program. This is the equivalent of Moonshot for President Kennedy, of going to the moon and returning safely within the decade. Well, we couldn't go to the sun. So we said, maybe we should just reduce the cost of electricity from sunlight down to $50 a megawatt hour within this decade. And so this was the cost. This white number out here is the installed cost, and this number out here is the levelized cost of electricity. So the first is the capital cost. And if you take the capital cost, put maintenance and amortize it over several years, you get a cost of electricity that you produce on a regular basis. And in 2004, it was about $400 a megawatt hour. In 2010, when we started the program, it was about $190 a megawatt hour, and the goal was to get to $50 a megawatt hour. Now, this cost out here can be broken into three parts. One is the module cost. The other is what is called the balance of system, which is installation, permitting, all kinds of things that goes into installing and getting it ready. And there's a third cost out here, which is power electronics, which is the inverter and all, to integrate it to the grid or to other systems. And our goal was to reduce these costs to about 50 cents per watt for the module, 40 cents a watt for the balance of system, and 10 cents a watt for the power electronics. And what you find immediately, which is interesting, is that the module is not the most expensive part. In fact, the module costs have come down so fast that today the lowest cost is about 70 cents a watt. It's almost at 50 cents, and it is very likely that we're going to get to 50 cents a watt by end of this decade. What has not come down as quickly is the balance of system. And that is still, it's about $1 something per watt or so. And that is where the big technology, the question is there a technology role play out here? And yes, there is. It's not just permitting, et cetera. There's some software that can be developed. But the name of the game in the future is how to reduce the manufacturing cost while increasing the efficiency of the solar cell to its max. So the question is, what is the limit? So this is now the efficiency of solar cells, and I won't go into the details of it. This is crystalline silicon. You can get production level crystalline silicon at about 23% or so, and the maximum is about 29%. It's slightly below what is called the Shockley-Quasar limit, but this is sort of the practical theoretical limit. It's about 29% or so. This is multicrystalline, polycrystalline silicon. These things are getting better and better. It's much cheaper in manufacturing cost. But their production level is about 14 or 15% or so. And there are ways to get those up to about 16, 17%. If they do, at much lower manufacturing cost because you don't have so much waste of silicon, this can get really, really very interesting. And there's, of course, copper, indium, gallium selenide, cadmium telluride solar cell, which is the cheapest today, is about 70 cents a watt. Today, the production level is about 14%. And if you can get to 17 or close to 20%, which means you need understanding of where the defects are, how the interfaces are, this is real engineering challenges that have to be solved to get them at the production level to 17, 18% or so. And so this is something which is very interesting, and we refer in this paper to some things that have been done out here. I see Eli out here, where they've taken gallium arsenide, taken it up to 29%, pretty close to the Shockley-Quasar limit. But gallium arsenide is very expensive, so they take this thin film and transfer it onto a low-cost substrate like plastic or some foil metal, et cetera. And that is the name of the game. How can you go to really high efficiency, in which case amorphous and all going to get you there? You need crystalline material, but you got to do it in cheap substrates. And that cheap substrate part is where the cost and the efficiency, that marriage is very important, and that's the name of the game for the future. When you have wind and solar, storage turns out to be extremely critical. And the cheapest way to store electricity at gigawatt-hour scale is pumped hydro. So you pump water up a dam, and this is, and that's about $100 a kilowatt hour. And that's the install cost. If you can go less than $100 a kilowatt hour, you are in business. And most of the techniques that have been there in the past, like compressed air storage, not in the cavities, but in artificial systems, or in flow batteries, et cetera, they were about $400, $500 a kilowatt hour. And we said, let's create a research program to bring down the cost. And that's where you need both the science, but the combination of science and engineering to build systems. Here's an example. There are many different examples. Here's one example from Yetmin Chang's group at MIT, and they spun off a company called 24M, where they've taken the best of the chemistry of lithium-ion battery and made it into a completely different architecture of a flow battery. And thereby, they are targeting the cost of $60 a kilowatt hour. Even if they get to 100, this is a game changer, because this is modular. You could scale it up, et cetera. Of course, there are science and engineering problems to be solved, but it's a very interesting architecture which seems to be scalable right now. Let me very briefly talk about the grid. The grid is extremely important, as we all know. We get our electricity from that. And we have about $1 trillion of assets on the grid today. And this grid is aging. And sometimes we get things like this. We had something in San Diego as well a few months ago. And there's a lot has to do with how we communicate information between different regions. but some of it has to do with the age of the grid. So just to give you an example, this is a distribution transformer, which is there in our substation, where you drop the voltages from hundreds of thousands of volts to a few hundred volts, and then you need other small transformers to drop it down to a few hundred volts if you get in our houses. This one is 8,000 pounds. It runs at 60 hertz, almost very similar to the design that Tesla and others had. The average age of the transformers in the United States is 42 years. And it's 2 years beyond the projected lifespan of these transformers. And we buy many of them from overseas, and there's a backlog. So imagine if some of these transformers blow out, we have a problem. If the circuit breakers don't work, we have a problem. So we said maybe there's a better way. Instead of just putting the same transformers back again, which is what is going on right now, maybe there's a better way to do it. And we created a program in power electronics, and there's some amazing stuff that is going on. Using wide bandgap semiconductors like silicon carbide or gallium nitride. Here is a single transistor, silicon carbide IGBT, that handles about 15 kilovolts of voltage and 100 amps. So 1.5 megawatts that it can handle on a fingertip, essentially. This is now the heart of the integrated circuit, if you may, of this device. And they're now trying, this was DC data, and they're now trying to modulate this at 50 kilohertz, not 50 hertz, 50 kilohertz. Because if you could do that, that whole transformer that you see, the inductor size will come down now. The whole transformer, instead of 8,000 pounds, will be about 100 pounds. You could put in a suitcase. And we believe that this is probably the future, whether it's silicon carbide-based or gallium nitride-based, et cetera. It's for the future of power electronics in DC-DC conversion, DC-AC. This could be the heart of reducing the terminal cost for high-voltage DC transmission, which is absolutely critical in many parts. And if that happens, that'll be more cost-effective than AC transmission. You know, Edison wins then over Tesla. Very briefly, let me talk about transportation. This is where the fuel consumption, U.S. fuel consumption is. Light-duty vehicles about 60%, trucks is about 22%, and the rest air, water, rail, pipeline, et cetera, and buses. Buses actually, buses are not that big. So the first thing, you heard about the CAFE standards that got approved. Boy, it took some time. We thought it would be much earlier. But it finally got approved a couple of days ago at 54.5 miles per gallon by 2025. So there's a ramp up of that, which is absolutely amazing. But the question is, how can we get there? Many ways of getting there. And if you look at the losses in a car, this is what the fuel energy is, and about 20 to 25% of that actually goes into moving the car. There's some thermodynamic losses, there are other losses, et cetera. And we all want to go from 0 to 60 in 5 seconds, right? That's what we want. And the question is, can we get there with being fuel efficient? And the way to do that, there are many ways to do that. One of that is to make lighter and lighter cars. And that needs new materials. So today, if you look at steel today, this is the elongation percentage of the ductility that represents the ductility of steel. And this is the tensile strength out here. Most of the cars are made by mild steel today, which is about 300, which means if they're low tensile strength, you need a lot of it to bulk it up, which is why our cars are so heavy. Now, you can get steels about 1,200 megapascals or so, but their ductility is not elongation is not very high, which is where we need research in steel. Now, this seems like old things, but it's absolutely critical to get to the micro and nano structures of these steels to make them more ductile and yet make them high tensile strength. Or you could get to carbon fiber composites, which is fantastic. It's just too expensive. By the way, BMW is scaling it, putting these composites in their cars right now at scale, which means the cost will come down. It's still at about $15 a pound. It needs to come down to $5 a pound, which means we need innovation in manufacturing in carbon fibers, not just the fibers, but the whole composite built so that you can integrate that. And that's where a university can really play a role in innovations in manufacturing to bring down the cost. And of course, we're not going to get rid of engines in the near future. They're going to be around for 10, 20, maybe more years. Maybe they're till 2050 or so. And combustion efficiency, whether this is spark ignition, this is compression ignition, and of course there are all kinds of research going on in homogeneous charge compression ignition engines as well, where you could go lean and still get the same amount of power. And so that's where combustion research comes in. So in terms of fuel efficiency, there's a lot of room out there but we need to reduce the cost. We need basic research and science and engineering in that. Let me say a little bit about trucking, because that's 20% of the fuel consumption. It so happens, this is an amazing story, that many of the trucks are now, long-haul trucks are converting to natural gas, in liquefied natural gas. Why? Because if you look at the extra cost for an LNG truck for the cryogenic tank or all the other peripherals that you need, it's about $100,000. But the price differential between diesel and retail LNG is substantial. In fact, retail LNG is about half the cost, half the price of diesel. And that fuel savings, the amount of driving that these trucks do, is sufficient that the fuel savings is $40,000 a year. So in 2.5 years, you have a payback period, 2.5 years, that it pays for itself. And this is on the truck side, on the demand side. On the supply side, each of these stations, this is clean energy fuel, each of these LNG fueling stations is $1.6 million. And their payback period is also 2 to 3 years. So we were asked to evaluate this, and we found that, heck, this is a business proposition. This is economically viable on the business side. The government should just get out of the way. And that is exactly what is happening now. This is the Clean Energy Fuels is putting up a whole infrastructure of LNG stations every 200 miles because the range of these trucks is not 1,500 miles, but it's about 300, 400 miles or so they can refill. And so that's what is going on, and this is economically viable, and we just stayed out of the way. The big challenge is, can we get natural gas into light-duty vehicles like automobiles that you and I drive? The big challenge is the infrastructure. If you look at the gasoline stations around the country, there are about 160,000 gasoline stations, and to create a CNG infrastructure like that is going to cost you $100 billion or more. And so the government doesn't have money to do that. So there's someone else has to. So the big challenge is storage. So it turns out 60 million homes have natural gas going into their homes. The question is, just like we're thinking about electric cars, could you recharge your natural gas cars at home? And it all comes down to the cost. Because you have to look at it as a system. You got the compressor, and you got a storage tank. If you want enough range in the car, 200 miles or so, you got to have enough of natural gas to be able to get there, which means you got to have enough of a pressure. Either you go high pressure, which means you have a multi-stage compressor and a carbon fiber composite tank, which is expensive, or you have a low pressure, which means the compressor is cheap, you get it off the shelf. But you need a sorbent material which can absorb the natural gas. So all the research that we did for hydrogen storage perhaps could be now used for natural gas storage at low cost, because this total system cost, if it is less than $2,000, your payback period is 5 years. And 5 years is a typical loan period for a car. So this is why we created an RPE program to reduce the storage system cost, which means you need research in both the science of how adsorption and others happen and the engineering to make a system to a period of 10 to 15 years, which is what it is today, to 5 years or so. Very quickly on biofuels. There's a lot of biofuel expertise out here. In fact, not most, all the biofuels today are photosynthetic. You got sunlight, you got carbon dioxide, you got water. And you use the sunlight in various forms, whether sugarcane, I'm simplifying it overly, sugarcane, corn, algae, or cellulose, and you can get to oil. Except for algae, almost all of them have an efficiency which is less than 1%. And that has to do with the Calvin cycle, the Rubisco enzymes, and all kinds of inefficiencies out there, and how much light we grab from the sunlight, from the solar spectrum. But it's less than 1% in most cases. So if you look at the cost, this is the projected cost 10 to 15 years from now. You can see the biofuels cost is about $120 per barrel or so. And most of it, if you look at around here, this is the feedstock cost. So it so happens that because the energy density, the efficiency of conversion is low, you need a lot of land to be able to capture the sunlight. And then you need to collect it. And this is light and fluffy. In fact, we use the terms light and fluffy in our paper. Not very scientific, but that's what it is. And so you need to be able to grab all that, and the larger and larger diameter you can get to, the better off you are, which means you need density. Now, there are various ways of doing it. You could do it this way, which is, you're trying to increase the radius of capture, but probably not the best way for the United States. Or you could do what Brazil is trying to do, which is mechanize this whole process. So you could take an engineering approach to it, Or you could take a science approach by saying that, could we alter the photosynthetic process itself? Could we increase the photon capture efficiency, which means you may have to go down to the antenna and do things with it? Or could we use some other cycles besides Kelvin cycle to do so? So here is a program that we created. Is that at the end of the day, energy density is very important. This is what we get from corn, 80 gigajoules per hectare per year. If you can get to 160 gigajoules per hectare per year at $50 a barrel, that would be game-changing. And so here's a program that we have, project is going on in Berkeley, with taking algae and the metabolic pathway in algae and putting it in a plant like tobacco. And so that in the future, if this is successful, you could squeeze the leaves of tobacco and get oil. I said this is great, this will be great, because I hope they're wildly successful, because then you'll have big oil and big tobacco coming and saving the world. You can't get better than that. Or you could have, these are loblolly pine trees which produce terpenes, and if you can increase the productivity of terpenes, it could be a completely new way of doing it. A completely new, just left field way of doing business, of making biofuels, is not using photosynthesis but non-photosynthetic microbes, by using reducing equivalents of hydrogen sulfide or direct electrons and CO2 or hydrogen, and putting in non-synthetic photosynthetic microbes and getting oil, and using cycles which are not Calvin cycle based but other reverse Krebs cycle. I won't go into the details of that. Potentially 10 times more efficient than photosynthetic process. And here is the first bottle of oil that will produce a biofuel without light. Electricity, electric vehicles, very quickly. You have today, the battery is the challenge. Today's batteries are about $600 a kilowatt hour of usable kilowatt hours, and it is heavy. So watt hours per kilogram is kind of low. What we really need to get to for all electric vehicles is about here. It's about $300 a kilowatt hour and about 180 watt hour per kilogram at the package level, which is about 400 watt hour per kilogram at the cell level. And we are seeing innovations. This is a battery from NVIDIA that we had funded, which are producing now 400 watt hour per kilogram at a certain charging rate with silicon-based anodes and very interesting layered compounds in the cathode. I won't go into the detail in the interest of time, but that is what is going on. This is already here, but there's a lot of work to be done to make it safer, to make it manufacturable, et cetera. But the first demonstrations of high energy density batteries is something that we're seeing right now. Let me just end with a few comments. When you look at the whole system again, you got R&D out here, you got manufacturing, you got commercial deployment, you got markets. You got to look at it as a system. We can't just do R&D and hope that things are going to go somewhere, because this is like a plane. You need the engine, you need the fuselage, you need the wings, you need the tail fins, everything all together. If you just have the engine, it's not going to fly. So this has to work together. And so if you look at where, as I said, the dollars required out here, this is where government R&D is in the early stages, but you need investments of these magnitudes from public and private capital markets. But you need markets for these to go. And here is where CAFE standards creates the markets for innovative technologies, for electrification and highly fuel-efficient renewable fuel standards. On the electricity side, the president proposed clean energy standards. Senator Bingaman has introduced it, but we don't have a bill yet that has been passed. And so there are some misalignments that we have. But appliance standards are tremendously powerful to get innovation of high-efficiency appliances into the market. They create the market. This is what regulatory policies are very useful for. But then you have financial policies where you have all kinds of investment tax credits, production tax credit. We don't have master limited partnership. We have it only for oil and gas and coal. We don't have it for solar and wind. These are tax policies. I won't go into the detail. That's entirely new talk. And there are other manufacturing tax credits that are there. And it turns out that many of these financial incentives are coming to an end. These are the financial incentives. Again, there's a whole list. I won't go into the detail. They're all coming to an end or have come to an end. We have misalignment in our technology. We get great technology innovation. So if you look at it, takes in the United States, it takes about 50 years for the United States to transition. We don't have that time frame. So the good news is that given sustained funding in R&D, we can and will innovate. That's no question. We have the best science and engineering infrastructure, and you all are out here. This is necessary but not sufficient. In addition to that, you need policies to align markets and finance with the tech innovation to accelerate the better solution. So let me end with this, but But we ended our paper with this quote: if we don't change direction soon, we will end up where we are heading. This is almost like a Yogi Berra saying, but that's what it is. Thank you very much.
So I know there's a lot of questions out there. I'm Dave Dornfeld from Mechanical Engineering, and I'm going to serve as the moderator for a few questions, and I'll turn it over to my colleague, Mark Asta from Material Science and Engineering, who will close the program. Dean Sastre had to leave for some important phone calls. So there are microphones floating around here. Questions, please keep your questions to a question, not a comment or an exposition. And we'd like to emphasize, of course, the innovative minds, which means the students first. Where are we? Okay, Don.
Hi, my name is Mike. I'm in electrical engineering. You said it's really important that the markets also support future innovation, and a big part of that is putting a price on carbon. And I'm wondering, now that you're maybe a little freer to talk, what are the possibilities of that in the future? Is there talk of that in the second Obama administration? Is it something that's being seriously pursued, or is it being dropped to the wayside?
You know, I have heard this from even my Republican friends in business, that they would rather have a price on carbon on a long-term signal so that they can adapt to it than not have anything, or have these fluctuating policies. The business wants certainty, okay, the business community. And they want certainty, they want a long-term. In fact, I think it was Bill Gates who in our summit said it very nicely. The price of carbon is absolutely critical. There's no question, because it creates the market. It's a regulatory policy that creates the market and shifts the landscape. You can have $0 per ton of CO2 today. What you want is a certainty that in 2020, 2025, 2030, this is the price of carbon that it's going to be. And if you could have that, just that, that'll give enough signal to the industry, the utilities and all the other industries, that it's time to change. And that's really what you need. And I'm certainly very hopeful that this will be taken up. This is, you know, if you ask in an administration how many things, big things can you get done in a 4 years, it's probably about 4 or 5. I certainly hope in the second term, which I hope he gets, it's one of those, you know, 3 or 4 things that is up there and really pushes hard. We can get it done.
Great question. Please state your, as you did your department and your year as well, if you could.
William Hagan, mechanical engineering. And in that same vein of his question, do you think that we would be more effective with a cap-and-trade carbon tax or a straight carbon tax? Or do you have any opinions on renewable portfolio standards like the one we have in California?
I think renewable portfolio standard is great. It creates a market. The challenge is the cost. That if the cost does not come down simultaneously, it becomes hugely expensive to address those mandates, renewable portfolio standards. So I think in addition to RPS, you need the innovation to bring down the cost. And that hand in hand will go a long way. Your first question was about, what was the? Cap and trade was, you know, either way will work. I've had, again, Republican friends from the business side, CEOs and chairmen of boards, et cetera, come and say that, you know, just make it simple, make it a carbon tax. Okay? It's a question of uncertainty on the amount of carbon versus uncertainty in the dollars that you're going to get. Okay? Those are the two uncertainties you're dealing with. So you got to take a pick. I'm kind of neutral to this. I think carbon tax would simplify things, but cap and trade has other benefits to it. Cap and trade has actually worked for SOx and NOx and other things. It's worked very well. And, you know, maybe you could learn from that and use it. I'm neutral. Let's get a carbon price. That's more important.
Let's take 2 more. One right here first.
Hi, I'm Michael Cohen. I'm a PhD in the Energy and Resources Group, PhD student. I was at the Hanford site in Washington over the summer, and where they built the first full-scale nuclear reactor to make plutonium for the atomic bomb, and I was just struck by the scale of the thing and how, you know, acknowledging that as an emergency, we really got it done. You know, there were 50,000 people there working on the reactor, you know, almost overnight. And I wonder, when I hear you talk about the length of time that these things are going to take and the need for investment in the private sector, I'm just wondering if, in your opinion, that is an inherently necessary or better way to get to where we need to go, or if it becomes necessary because we're not treating the situation as a national emergency and throwing, the magnitude of public resources at it that some of us might prefer.
Well, since you said Hanford, in fact, I'll be there next week for the cleanup. And I hope we do it better this time, because the amount of money that is spent, it's tens of billions of dollars in trying to clean up the mess that was created in Hanford. And I thought I'd left DOE, but the Secretary of Energy pulled me into this committee now to help in reducing and finding innovative ways to reduce the cost of the cleanup that we have. I certainly hope in the future, yes, there's a national emergency. We perhaps, I wouldn't like to call it an emergency. Emergency is a very strong word. I think we have an urgency of doing things where, if we don't move fast, if we don't take the leadership position in the world, someone else will. And in fact, in this alignment of markets, finance, and technologies, well, China is doing pretty well in aligning the markets, in creating, whether it's feed-in tariffs or other things for solar, and creating incentives for manufacturing, et cetera. They're aligning all that right now. So we better get our act together. But I would rather do it in a much more sustainable way than perhaps what was done in Hanford. But it was done based on an emergency.
Last question. Sure, right here.
I read a couple days ago. First of all, my name is Ryan. I'm a mechanical engineering major with a focus on energy. And I was wondering if you'd read Amory Levin's response to your article, or Reinventing Fire, and what you thought of it. Because they seem to be pretty similar, but...
Yeah, actually, we had that in our paper earlier. So I should respond to Emery about this. We had that, the fact that when you get lightweighting, when you get smaller engines, you could redesign the whole car. You could revisit the design of the car itself and get secondary benefits which are as important as the primary ones. We actually had that in the paper. Because of space, we had to take it off. So I must apologize to Emery about that. But he and I have chatted about this in the past.
Great. Thank you once again.
Thanks a lot.
Okay, so this concludes today's View from the Top, and we want to thank Arun, and as a small token of our appreciation, we want to give him this little gift, and the purpose there is to reconfirm his status as a Berkeley engineer, as you can see.
I'm so glad. Thank you. I'm so glad I lost weight, and it's not an XL, but an L.
Okay, so just before we leave, I want to thank once again Tau Beta Pi Engineering Honor Society for helping us to put this on. And we hope to see all of you on September 12th for the next View from the Top. And so with that, goodbye and go Bears.